The other calculation that we'll encounter is to calculate the value of the rate constant with its units from a set of experimental data. We have the rate law, and the first thing that we're going to do is to rearrange that rate law to solve for k. What I'm also going to do in this example is I'm going to solve for the value first and just ignore the units, and then we're going to rewrite everything and figure out what the units are. I think it's generally easier that way. Starting with the rate that I've highlighted, if we rearrange that to solve for k, we end up with k equals rate divided by the concentrations. So we have a raised to the 1/2 times b squared. Calculating the value really is as simple as just plugging the numbers in. Our value of rate is 1.47 times 10 to the negative 3 divided by 0.100 raised to the 1/2 times 0.150 squared. Keeping track of our sig figs, we have 3 sig figs for rate and 3 sig figs for each concentration. So our value will be rounded to 3 sig figs. And when we do the math, we end up with 0.207. To figure out the units, we're going to use the same rearranged equation, only now we're only going to plug in units. The other thing we're going to do is we're going to write each part as a separate term with its own numerator and denominator. That way the units will cancel more clearly. So we have k equals rate. Rate has units of moles per liter second. And I do encourage you to expand the units of molarity here for purposes of cancellation. We have A in the denominator, which means the moles will be in the denominator and the liters will be in the numerator. This is raised to the power of 1/2, so we're going to put that exponent by each part of the units. And then we have B, which is also moles over liters, starting in the denominator. And what I tend to do if I have a squared or a cubed term is I will just write that out twice. And I will label these in just a bit. For me, it's easier to cancel the units and not make a mistake. Now, if you are 100% comfortable combining and canceling units that have fractional coefficients, then you may be able to approach this more concisely, but we'll work it out this way here. Let me label my terms. So this was my rate, this was my A, and both of these were B because of the squared term. So that's the only time that I will replicate one of the terms is if it's a squared or a cubed. If it's a 1/2, then I will actually incorporate the fractional coefficient. Next step is we're going to cancel what will clearly cancel. And what I mean by that is moles will cancel moles and liters will cancel liters. So I do that type of a cancellation for as many terms as I can. And then if I'm left with a fractional coefficient, if I'm still not done, like we have here, then what I do is I rewrite any whole number coefficients as fractions. So I do have a liters raised to the 1 and a moles raised to the 1. So I'm going to write those as 2/2. That way they will more easily combine with the 1/2 that I already have. So combining these units, in the numerator I have 1/2 plus 2/2, so liters to the 3/2. In the denominator I have seconds, and then I have moles to the 1/2 plus moles to the 2/2. So 1/2 plus 2/2 equals 3/2. And then I can combine the moles and liters into molarity. In this example, because the moles is in the denominator, then that means that I will write this with a negative exponent. And so I end up with molarity to the -3/2 times seconds to the -1. So my final result for K is 0.207 molarity to the -3/2 seconds to the -1.